Hi guys, welcome to this video. This is a second video on this particular paper of OCR Physics A May 2022 for the first paper, which is the modeling physics. And in my previous video, I've already covered section A, which is the multiple choice section of this paper. So in this video, we'll be looking at section B, which is basically the long answer questions. So let's get right to it. Question number 16a, it says, describe how an experiment can be carried out to determine the force constant of an elastic cord in the lab by plotting a suitable graph. You may assume that the cord obeys Hooke's law. Okay, so according to Hooke's law, we know that force is equal to the spring constant times by the extension. So if we want to get the force constant or the spring constant, we can simply draw a graph of force versus extension and basically get the gradient. So to work out the extension, all we need is just basically use some weights, okay, hang the weights onto the cord and measure the extensions using a meter ruler and then draw your graph, okay, and then get the gradient. So let's write this all down, okay, so I'm going to say that use different weights or masses on the cord, measure the extension each time using a meter ruler, and then from there you can basically record these values and plot a graph of force versus extension, and the gradient of this graph is going to be the change in F over change in X, which is basically the force constant. Alright, so that's part A done. Okay, let's move on to part B. It says a simple catapult is made by elastic cord fixed to two supports, like so, and the unstretched length of the cord is the same as the distance between the supports. The distance that the center of the cord has been pulled back by is d, and the cord has a force constant of 500 Newton per meter. Okay, let's check out the question. So they've drawn a graph of extension versus distance, and it says that a small ball of mass 30 grams is placed at the center of the cord and drawn back with a distance of 10 centimeters. The ball is then released and launched horizontally from a height of 1.5 meters above the ground. Use the graph to show that the elastic potential energy in the cord is about 1 joule. Okay, so we know that elastic potential energy is given by the formula half kx squared. Now, so all we have to really do is, using the graph, figure out what that extension is, and we are already given the spring constant, which is 500 Newton per meter. So we're going to check out what the extension is at 10 centimeters of distance, which is right in the middle. So that's your 10 centimeters, and that is right bang in the middle, which is nice and easy. So this is 6 centimeters, okay, on the graph. So I'm just going up and across. And so this one is going to be half times by 500 times by, don't forget to convert 6 centimeters into meters. So that is going to be 0.06 squared. And once I pop that in the calculator, I end up getting a value of, it's going to be 0.90 joules, which is approximately 1 joule of energy. Okay, so for the next question, for the next part, we are to show that the maximum speed at which the ball leaves the catapult is about 8 meters per second. Okay, so this is all about conservation of energy. We know that the elastic potential energy is essentially maximum at the point where the string this cord is being pulled. Okay, so you have like a ball over here, right over, let's just draw it in a different color. So you have it right over here, and at this point in time, it has maximum elastic potential energy. Now, as the ball is released horizontally, it will have, therefore, kinetic energy. and therefore we can say that the kinetic energy, which is half mv squared, okay, so EP is converted or transferred into EK, we can say that because we know EP is 0.9 joules, okay, that is equal to half mv squared, and we can then calculate the maximum velocity with which, or the speed with which, the ball is released. So the speed is the square root of 2 times 0.9 over the mass, which was given to us as 30 grams. Okay, so 30 grams is 0.03 kilograms, and that gives me a value of 7.74, okay, which is 7.7 meters per second, and if you were to write this down to one significant figure, it would have been 8 meters per second. So far, not so bad. Okay, let's move on to the next question, part I. In this question, we have to calculate the horizontal distance r travelled by the ball before it strikes the horizontal ground. Ignore the effects of air resistance in your calculation. So we can use SUVAT, and a very simple formula of distance is equal to the initial horizontal speed, I'm just going to put it ux, times by the time. We already know the horizontal speed is what we calculated in the previous part of 7.7 meters per second. So all we have to do is figure out the time using SUVAT. Okay, so let's put that into what we are given. We are given that the height is 1.5 meters above the ground. It starts from rest, okay, we know that the vertical, if I just say vertical velocity, initial vertical velocity is 0, because it only is released horizontally, okay, it doesn't have a vertical component therefore, and V is, well, we don't really know, okay, so I'm just going to leave it. A is 9.8 meters per second squared, and T is what we are aiming to find. So S is equal to UYT plus half A, or rather GT squared, and this just basically becomes 0, and therefore T is the square root of 2S over G, okay. In other words, it is 2 times 1.5 over 9.8, which gives me a value of a 0.55 seconds. Lovely. So now from here I can simply calculate R, which is the velocity of the speed of 7.7 meters per second times by 0.55 seconds, and that gives me an answer of 4.26, or simply 4.3 meters. There we go. So for the next part, explain how the value of R can be calculated in the third part compares with the actual value. Now, in reality, there would be some air resistance, okay, and so the velocity will be lower, okay. We know that the final horizontal velocity will not be the same as the initial horizontal velocity. So that means that the distance travelled, R, okay, will be actually smaller, okay. So I'm going to say, for 2 marks, I'm going to say that the actual R value will be smaller because Vx is, well, not equal to Ux, okay, as air resistance will cause the ball to slow down, okay, slow down. So that will be my answer to the last part. Hopefully that's the last part of this question. Let's move on to question number 17 now. So we are given that an electric engine of mass 17,000 kilograms has a constant power output of 280 kilowatts, and it can reach a maximum speed of 42 meters per second on horizontal rails. The maximum kinetic energy of the engine is 15 megajoules. Okay, the engine is initially at rest, and show that the minimum time taken for the engine to reach its maximum speed is about 1 minute. Okay, so because we are given power output and we are given the energy output as well, we can simply use power equals energy divided by time. So this means that time is energy, which is 15 million joules, divided by the power, which is 280 times by 8,000 watts. So once you pop that in the calculator, you will end up getting a value of, okay, 53.6 seconds, or, well, 54 seconds, okay, if I was to round this down. And this is very close to a minute, okay, so this is basically a 0.9 of a minute, okay, ninth of a minute, I mean. Okay, so 9/10. Okay, so anyway, that is close enough to what we want. So part B is saying that the engine is moving along the horizontal rails at the constant maximum speed of 42 meters per second. The weight of the engine is W, the total normal contact force from the rails is N, friction is F, and F is responsible for the motion of the engine to the right. Okay, complete the free body diagram for the engine by showing a missing force and the magnitudes of all the forces, and we've been given some space. Okay, so now we know that the force that's basically missing is going to act towards the left, okay, just equal in magnitude, okay, as F, so just gonna draw it up to here, and that is going to be the force, okay, that's missing. Now, we need to figure out what these numbers are, so let's start off by perhaps working out this force which is provided by the engine, okay, it's the frictional force which is basically equal and opposite to the one that's provided by the engine actually. So we can say that power is equal to force times by velocity, and therefore V is power, which is 280 times by 1,000 divided by the, sorry, I was meant to find the force, not the velocity, my bad. So that's going to be over 42 meters per second, and that will give me a value of, okay, 6,700 newtons to two significant figures, so that is there, okay. And then for the weight, we know that it's just mass times gravity, so the mass was given to us as 17,000, if I'm not mistaken. Let's just double check. Yes, 17,000 times by 9.81, and that gives me, again, roughly, well, two significant figures. It gives me 17,000. Okay, that's that, and therefore the normal force will also be of the same magnitude, and there you have it. So let's check out the next part. Okay, so in part C, the speed of the engine is 42 meters per second. The driver sees an obstruction 167 meters from the front of the engine. The engine is switched off and the brakes are applied. The constant force opposing the motion is 120 kilonewtons, and the reaction time of the driver is 0.4 seconds. Show with the help of calculations that the engine will stop before reaching the obstruction. So we need to basically prove that the stopping distance, okay, is less than or equal to 167 meters. Okay, in fact, it should be less than, because it says before. Okay, so let's work on that. And we know that stopping distance is made up of thinking and braking distance. Okay, so if we can figure those two distances out, thinking distance and braking distance. Okay, so let's figure out the two distances and add them together. So for thinking distance, it is simply the speed with which it's moving times by the reaction time. That's really simple. And that it's moving at a speed of 42 meters per second. So 42 times by 0.4 seconds. And that would give me a value of 16.8 meters. Okay, so that is my thinking distance. Okay, now I need to work out the braking distance. So for that, let's put an arrow down here. Okay, so I know that as the brakes are applied, the work done by the brakes is converted into slowing it down, or well, it's transferred into the kinetic energy store. Okay, so work done will help me figure out the distance moved, the braking distance involved. Okay, so we know that work done is force times distance, and we know kinetic energy is half mv squared. So we know that the force applied, okay, opposing the motion, is 120 kilonewtons. Okay, so distance is therefore 0.5 times by 17,000 times by the speed with which it's moving, okay, 42 squared, over the force, which is 120,000 newtons. So that's quite straightforward, and it ends up giving me a value of 125 meters. And so if we put them together, the stopping distance is going to be equal to 125 plus, let's say 17, okay, and that is 142 meters, which is less than 167 meters. So yes, it will slow down before reaching the obstruction, stop before reaching the obstruction. Cool. Right, let's move on to our next question. Righty. Okay, so we have a tent which is secured by 3 ropes along each of its long sides, and we've been given some dimensions. We'll keep that in mind. It says for part A that wind of speed 12 meters per second blows at right angles to the shaded side of the tent for 3 seconds, and the density of air is 1.2 kilograms per meters cube, and we need to show that the mass of the air which hits the tent in this time is about 490 kilograms. Okay, well, that's fairly simple. Let's look at the formula of density first, okay, because that relates the mass and the volume. So density is m over v. So if we can figure out the volume, we can figure out the mass. So I would work out the volume of the air that's hitting the tent, okay, on the shaded area, which involves this rectangular area. Okay, so the area of this rectangle is 6 times 1.9 meters squared, okay, which will give me a value of 11.4 meters squared, okay. And we also know that the air is, or the wind, is traveling a distance of 12 meters per second and 3 seconds. So it's traveling a distance of 36 meters, okay, altogether. So that means we can figure out the volume, okay, from these two numbers, 11.4 times by 36, and that gives me a value of 410.4 meters cube. Okay, so I've got my volume and I've got my density. I can work out the mass by simply doing 1.2 times by 410.4, and it gives me an answer of 492.48 kilograms, which is 490 kilograms to 2 SF. Okay, so not too bad. Right, so for this part II, all of the air incident on the shaded side of the tent is deflected at 90 degrees to the original direction. Use the information given in part AI to calculate the magnitude of the force F exerted by the wind on the shaded side of the tent. Okay, so, well, what I'm going to use is Newton's second law, which is the rate of change of momentum. Okay, that's delta P over delta T. Why? Well, because I know that I've been given the mass of the air. Okay, well, I've just calculated that, and I know the speed, okay, in part AI. Okay, so the speed is 12, okay, meters per second, and I know the mass is 492.48 kilograms. And this is happening for 3 seconds. Okay, so let's put them down into our formula. So mv minus u over t, and 492.48 times by 12, well, minus 0, okay, divided by 3. So that is going to end up giving me 1,969.92 newtons. If you round this to one significant figure, that'll be 2,000 newtons. Okay. For part B, it says when the wind speed exceeds 20 meters per second, the ropes securing the tent break. Okay. Describe and explain in terms of forces how the ropes and the shape of the tent could be modified to withstand wind speeds exceeding 40 meters per second. Okay, so you want to double the speed. They're talking about doubling the velocity. So we just have to think about the forces, okay, and link the force with the shape, okay, of the tent. Okay, so basically, and also the ropes. Okay, we can talk about how this change in speed should modify our ropes design. Okay, so or the material used, for example. Okay, so this is all about the materials section of your OCR Physics A textbook. Okay, so I'm gonna of course explain this, I think, in bullet points because it just makes more sense in my head. So I know that as the velocity is doubled, the mass of the air, or mass of the wind, hitting the tent per second also doubles. And we know that since delta P is m times delta V, the momentum quadruples, increases by 4 times. Okay, and so does the force, right? And so does the force exerted on the tent, as obviously force is directly proportional to the change in momentum. Okay, the time remains the same. So in order to withstand these winds, you need to quadruple the cross-sectional area of the ropes as well. Okay, so that's one of the changes that we should make. Okay, so to withstand these winds, the rope's cross-sectional area must be quadrupled. Okay, and secondly, we can change the materials of the rope such that it can handle it can handle 4 times as much breaking stress. Okay, so we can use stronger, more durable material with high ultimate tensile strength. Okay, and that would be helpful to also withstand these winds. Okay, so I will add that to this point. So plus using a different material for the ropes, so that, well, with 4 times higher ultimate tensile strength, okay, UTS, so that it can handle speeds of 40 meters per second and above. Okay, so I would say that it should be at least 4 times higher tensile strength. Okay, so with at least. Okay, so that's to do with ropes. Okay, so we've changed the cross-sectional area, increased it, and also changed the material. Now let's talk about the shape of the tent. So we can certainly change that. Okay, so I'll just explain that using the diagram. So shape of the tent, well, it should be more streamlined. So at the moment, the winds are hitting right at 90 degrees, okay? And if we can make the shape more streamlined to lower the impact force and thereby changing the angle at which the the winds are hitting the tent. Okay, so rather than hitting at 90 degrees right straight up, if we could, put the tent maybe at an angle. Okay, so as the winds are hitting, okay, like so, if we can perhaps talk about that angle, what that angle could be, okay, we know that the winds will basically be directed at an angle, and that will also lower the impact force. Okay, so the momentum will also be reduced. Okay, momentum and force are affected by the same amount, which is 4 times. So if we could lower the momentum or the force by 4 times, we will be able to get that angle. Okay, so I'll just say that first of all, the shape of the tent should be made more streamlined in order to reduce the impact force, and the angle, okay, the angle, I don't understand why they put this down, like they just make you feel like as if you're using more space. Hate that. Anyway, sorry. Anyway, we have to talk about the angle, right? So angle of the tent should be made less than 90 degrees in order to reduce the impact of higher winds. And if I just use a diagram here, so as I was saying earlier, you have the change in momentum, initially, what was the change in momentum? Let's just see. Or the change in force, I guess I'll use that. So if I had this much force, impact force, okay, and basically you wanted to reduce it by a factor of 4, okay, essentially, I guess it doesn't matter if this was basically, if this is, say, 19,600 newtons, okay, and you wanted to make it angular, let's call this theta, okay, and this value, if you just sort of half it, roughly about 4,900 newtons, okay, so just, sorry, not halving it, I mean dividing it by 4, my bad, okay, so that force is essentially sine inverse of a quarter, okay, because you are quartering it, okay, and that would give you a value of 14.5 degrees. Okay, so that's roughly about 15 degrees. Okay, so if we could make the angle about 15 degrees instead of 90, we will be able to reduce the impact force by a factor of 4. Okay, so that is what I would say for the last point. Hope this makes sense. Okay, let's move on to our next question now. Okay, so for question number 19, we are given in part A, a fixed mass of nitrogen changes phase from liquid to gas at constant temperature. Okay, so explain the change in the total internal energy of nitrogen. So we know that internal energy comprises of sum of all the kinetic energies and potential energy. So I'm just going to write it down as sum of kinetic and potential. Okay, the examiner will surely understand. And as it's a changing state from liquid to gas at constant temperature, we know that kinetic energy remains constant. Okay, remains constant. But EP increases. So internal energy also, therefore, increases. It's just 2 marks. Okay, fairly simple question. Okay, so for part B, we're given that in a factory, nitrogen gas is added to packets of food to keep it fresh for longer. In 1 hour, the factory uses 15 meters cube of nitrogen at a pressure of 100 kilopascals and temperature of 23 degrees Celsius. Show that the number of moles N of nitrogen used per hour is about 600. Okay, so we know our ideal gas equation, which is N equals PV over RT, and we're given everything over here, which is pressure as 100,000 pascals, volume is in meters cubed, which is nice and easy, divided by the value of R, which is a gas constant, 8.31, times by the temperature, which is 23 degrees Celsius. So make sure you add 273 to it to make it into kelvins. Okay, so that would be 296 kelvins, and once I pop that in the calculator, I end up getting okay, 609.8, which is fabulous because that is, yeah, the same as what we wanted to prove. Okay, righty, moving on to part II. Calculate the mass of nitrogen gas used in 1 hour. Okay, we're given the molar mass of nitrogen, and this is a really simple question for anyone who takes chemistry for A levels. Okay, we know that mass equals Mr. Moles. Okay, and MR, which is the molar mass, is given to us in kilograms, which is what we need in physics. Okay, and times that by the number of moles that I just found. I'm going to use the unrounded value, and that would give me an answer of 17.1, or just 17 kilos. Okay, so for the next part, III, the volume of nitrogen being used cannot change. State how the rate of mass of nitrogen can be reduced. Okay, so we want to change, or we want to reduce the rate of mass. So volume cannot be changed. Now we know that PV equals nRT. In other words, it's M over MR times RT. Okay, so what we want to do therefore is, because we are relating mass, okay, we don't want to consider volume because it can't be changed. So if we want to reduce the mass, we therefore want to reduce the pressure, okay, or we can also increase the temperature, right, because the temperature and the mass are inversely proportional to one another. So because it's just 1 mark, I'm going to just mention either to decrease the pressure, okay, or to increase the temperature, as I'll just stick to pressure, okay, as M is directly proportional to P. Okay, so that's basically my answer there. Okay, for part number 4, we are given that nitrogen at the factory is stored as liquid. The liquid expands at constant temperature to form gas in a short section of a pipe. When the air temperature is 0 degrees, a thick layer of ice is formed on the outside of the pipe from the water vapor. Okay, that's important. And in 1 hour, the mass of ice formed is 1.3 kilos at a temperature of 0 degrees Celsius. We need to use the data below and your answer to part B, II, to estimate the specific latent heat of vaporization of nitrogen. Okay, so essentially what's happening over here is that you have, let's say you have a little cross-section of a pipe which has liquid nitrogen in it, and around that liquid nitrogen we have air, or we have the water vapor in the air, okay, and that's in gaseous state. So you have lots of these water vapor molecules, and what happens is that they are condensing to form ice. Okay, so they end up forming, so just imagine that they're on either side, so they end up forming a thick layer of ice, okay, which is basically the solid form of water. And so the energy is essentially transferred from this water vapor turning into ice, and then the ice giving the energy to this liquid nitrogen, that this liquid nitrogen turns into gaseous nitrogen. Okay, so at the same temperature, the temperature does not change, so this is where we use latent heat of latent heat. So if I just write down an equation in terms of the latent heat of nitrogen, so M of nitrogen times by the latent heat of vaporization, and that's what we are trying to find here. So this energy transferred is from the H2O. Okay, H2O molecules, gaseous molecules. So we're going to take the latent heat of vaporization of water and the latent heat of fusion of ice. Okay, so that will be M of, let's say, H2O times by the latent heat of vaporization, okay, plus the M of H2O, or you can say ice if you want to, which is going to be that of fusion, and all that divided by the mass of nitrogen that we found in the previous part will give us the latent heat of vaporization. So if I just put all the numbers in, we know that the mass of water and the ice, they're the same, okay? Given that all the water vapor condenses into ice, it is going to be 1.3 kilos times by the vaporization heat, which is 2.26 times 10 to the 6, plus the fusion, which is 3.34 times 10 to the 5, and all divided by the mass of nitrogen, which we calculated to be 17 kilograms, so just popping that there. And once you put that in the calculator, you end up getting an answer of 2.0 times 10 to the 5 joules per kilogram. Okay, so for part A, it says, for a simple harmonic oscillator, the acceleration A is given by the equation that, where omega is the angular frequency and x is the displacement. Show that this equation is homogeneous by reducing both sides to SI base units. Homogeneous means, well, same units. Okay, so we need to prove that it is the same units on either side of the equation. So we know that for the left-hand side, the unit of A is meters per second squared. This is the most simple unit, base unit therefore. And for the right-hand side, we know that the units involve that of omega squared and x, okay, the displacement. So omega squared is just per second, okay, squared, per second squared, okay, as it's basically like so, okay, because it's squared, right? Times by x, which is the displacement in meters. So yes, they are the same and hence they are homogeneous, okay? So that's what I'm going to say. LHS is equal to RHS in terms of units. Cool. For part B, we are given that the diagram shows a glass U-tube partially filled with a mass of water. One end of the U-tube is connected to a gas supply at constant pressure and the other one is open to atmosphere, okay? The displacement of the water from its equilibrium position is x, the density is 1000, that of water, in kilograms per meter cube. The pressure of the gas supply raises the water in the U-tube. The vertical distance between the two levels of water in the two vertical sections is 10 centimeters, okay? And we need to calculate delta P, which is the difference in the pressure of the gas and the atmosphere. Okay, so because it is fluid pressure that we're talking about, delta P is rho GH, okay, and therefore it is just 2 marks, okay, it's really simple. So the fluid pressure is 1000 times by 9.81 times by the height or the vertical distance, okay, which is 0.1 meters. So that gives me 981, or quite simply 980, to two significant figures. Okay, so next up, we've been given that when the gas supply is disconnected, the water levels in the U-tube oscillates with simple harmonic motion. The acceleration of the water level in the left-hand side of the U-tube is given by this equation. Okay, where m is the mass of water, a is the internal cross-sectional area of U-tube, rho is the density of water, g is the acceleration of free fall, and x is the displacement of the water level in the left-hand side of the U-tube. Okay, for this U-tube, a is equal to that and m is that. Show that the period t of the oscillations is 1 second. Wow, okay, amazing, I love it. So I know that acceleration is also equal to minus omega squared x. Okay, so if I equate them, I know I can replace, the reason why I'm using this is because I know that omega is 2 pi over t. Okay, where t is the time period. So I can involve time period, I can find time period by using, well, the equation given and the equation I know. Okay, so minus omega squared x is equal to minus 2 rho ga over m x, minus and minus cancels, x and x gets cancelled. Omega squared is 2 pi over t squared, and just putting everything in a tidy form. Now, if I just flip the sides, square root, appropriately, I'm going to end up getting, I'm just cutting through some steps, okay, but I'm going to end up getting, as you'd appreciate, 2 pi times by the square root of m over 2 rho ga. Once I put all the numbers which I am given Okay, so m is the mass, which is 0.052 over 2 times 1000 times 9.81 times by the area, which is thankfully in meters squared, 10 to the minus 4. Okay, and I would end up getting a value of 1.02 seconds. Fab. Okay, that's about 1 second there. Okay, let's see. Question number 2. Well, question number 2, alright, well, part 2. The oscillations of the water level are slightly damped. Okay, damped meaning that, well, they are experiencing some resistance. And so the amplitude is not going to be the same. And at time t equals 0, x is 5 centimeters. Sketch a suitable graph of the displacement x against time for the oscillating water level at suitable values to the time t-axis. Okay, right. So we know that the time period is about 1 second. Okay, so I'm going to take 1 second as a rounded value rather than 1.02. It's easier. So if I just split this up into, say, 0.5, that will be then 1, that will be 1.5 and 2. Okay, I know that it has to make a complete wave in that 1 second. So starting off with 5, okay, so it will be really bad, but oh well. Oh my word, can't do it. Okay. So as long as it's decreasing in amplitude is what we are concerned with. Okay, that's what the marks are for. And that's basically, it's not very accurate, guys. I'm sorry. I'm just going to try to make it a little bit better. Give me a sec. So, okay. So, perhaps just pretend that it reaches the top. Okay, so, nope, I'm really bad. Let me try again. Sorry. Okay. And okay, let's just stick to that one. Okay, so obviously in the exam I would be more careful doing it in pencil as well. And just by the eye we can say that the amplitude is decreasing as the oscillations are damped. Okay, so for my question number 3, it says that the U-tube is now connected to another gas supply where the pressure oscillates at frequency of about 1 Hertz. Okay. Explain the effect this will have on the water in the U-tube. So, because this applied frequency, the driving frequency, is approximately equal to the frequency here, right? Because the time period is 1.02 seconds, so frequency is also going to be roughly about 1 Hertz. That means that resonance will occur and the amplitude is likely to increase to a maximum. Okay, so I'm going to say that the applied frequency is approximately equal to the natural frequency of 1 Hertz. So the amplitude of the oscillations of water will increase perhaps to a maximum, okay, because it's still not like 100% the same, it has to be the same, so but the chances are that it would be almost very close to a maximum. Okay, so there would be an increase in the amplitude, that's important to say. Okay, right, let's move on to our question number 21 now, where it says in part A that a nebula is a giant cloud of gas and dust in space. The nebula can produce a star over a long period of time. State what causes the initial collapse of the nebula. Well, it is gravitational force. So gravity pulls it inwards. So that's that. For part B, it says a nebula X is modeled as a sphere of gas and dust particles of diameter 6.4 pc, okay, which is parsec, okay, and the nebula has 1.0 times 10 to the 12 gas particles, gas and dust particles per meter cube, with a temperature of 250 kelvins. The nebula behaves like an ideal gas. Show that the volume of the nebula is this much, okay, where 1 parsec is 3.1 times 10 to the 16 meters, okay. So to work out the volume of the nebula, we're assuming that because, well, it is a sphere, okay, V is 4/3 pi r cubed, where r is in meters, okay. So we're given that the diameter is 6.4 parsec, so the radius is 3.2 parsecs, okay. So 3.2 times pi, 3.1 times pi, 10 to the 16 meters cubed. And once you pop that in the calculator, you end up getting 4.1 times 10 to the 51 meters cube. That's humongous. Anyway, II. Calculate the total kinetic energy of the gas particles and the dust particles in the nebula. So we know that kinetic energy is, given that it's an ideal gas, is equal, it's directly proportional to the temperature, and it's given by 3/2 kT. Okay, so that will be 3/2 times by 1.38 times 10 to the minus 23 times by the temperature, which is 250 kelvins. Okay, however, it is the total energy that they're talking about. So you must times it by the number of particles that you have. Okay, I'm just going to call it N, capital N. Okay, the number of particles given to us of the gas and the dust were 10 to the 12. Okay, and per meter cube. Okay, so that's what I got to use up over here. All right, so that will be times by 1 times 10 to the 12 per meter cube, which means I have to use the volume that I just found out from here. Okay, so 4.1 times 10 to the 51. And so that is going to leave me with still a really big number. Okay, and it gives me 2.1 times 10 to the 43 joules of energy. Okay, so that's that. And I'm just going to put it down here. Cool. Right, let's move on to part C. It says that the nebula that formed the Sun is estimated to have a diameter of 3 parsec and had a similar composition to nebula X in part B. The mass of the nebula X is much greater than that of mass of the Sun. Calculate the ratio of the mass of nebula X divided, to the mass of the Sun. So if I know that, I'm given the diameter, yes, so diameter is related to volume, volume is related to mass, and we know that density is mass over volume. So if we just say that if the density is constant, okay, then the mass is proportional to the volume, which is then proportional to r cubed, okay, or diameter, it doesn't matter, okay, because you're just changing the proportionality. Okay, so because the diameter of the previous nebula X was 6.4 parsec, and you simply have to cube it, divided by the diameter of this, okay, which is 3 with the Sun, okay, and that's 3 cubed, okay, and that ends up giving us 9.7 as the ratio. So let's check out the next question now. After a long time, nebula X will form a stable star. Describe the eventual evolution of this star. So we know that when all the hydrogen runs out, or hydrogen turns into helium, it deviates from main sequence. Okay, and depending on how big it is, it would have two different sort of parts. Okay, so because this star, this nebula, is bigger than the Sun, it will form a red supergiant. Okay, turns into a red supergiant as the mass of nebula X is greater than that of Sun. Okay, and then it will likely explode as supernova, and leaving behind either a neutron star or a black hole. Okay, so that brings us down to 22A. which says that a team of astronomers have measurements to determine the peak surface temperature T and the luminosity L of a distant star. They plan to use Stefan's law to estimate the radius r of the star, explain whether the astronomers should attempt to measure T or L more accurately, or sorry, more precisely, to reduce the uncertainty in r. Now we know that according to Stefan's constant, law, L is equal to 4 pi r squared, the constant, times pi t to the power of 4, okay? And because the uncertainty due to the temperature T will result in 4 times uncertainty as much as due to L, luminosity, therefore they should aim to reduce the uncertainty in temperature, hence measure the temperature more precisely, okay? So since that's the case, uncertainty due to temperature will result in 4 times as much as due to L, okay, because it's to the power of 4, remember, for percentage uncertainty we always times the resultant by 4, okay, that's, whereas L is just to the power of 1, so that's just going to be higher uncertainty due to temperature. So they should measure T more precisely. Okay, moving on to our part B, which says that it is suggested that the luminosity L and the mass m of a star can be compared to the Sun by the equation given to us, where L with a little dot, okay, like so, is the luminosity of the Sun, and that represents the mass of the Sun, and the value of B is between 3 and 4, okay, which is a constant, right? So let's see, we're given some information about 5 different stars, and also given a diagram, a graph, and let's check out what the question is asking. Okay, so it says luminosity of a star is directly proportional to the rate of fusion of hydrogen nuclei. Okay, use figure 22 to determine B and use your knowledge of HR diagram to deduce how the lifespan of hotter stars compares with that of the cooler stars. Okay, so I think this is a really nice, simple yet long question. As a last question, I believe this is the last question. Oh no, there's another one, sorry, ignore me. Anyway, so what I'm going to do is basically look at my diagram and the equation and see how I can figure out the value of B. Okay, so I am given an equation, okay, which relates to this graph, as this graph is, it contains log, okay, on both axes, which is really good because we can, once we turn this given equation into a logarithmic equation, we end up getting an equation of a straight line. Okay, so in order to do that, I'm going to just do a bit of maths over here just to be very clear that I'm going to log both sides first. Okay, so just to explain this. So log of L over L naught, just going to call it that, is equal to log of M over that of the Sun to the power of B. Now, as per the log rules, B will come in the front, okay, because B is a power. So B log of M over mass of Sun is equal to that. Now, if we compare this with the equation of the straight line as per the graph, okay, given to us, then we can say that this compares, okay, comparing this to y equals mx plus c, okay, we can safely say that since this is on the x-axis, the number or the letter in front of it will be the gradient. So m or b is the gradient. Okay, so gradient can be calculated. So let's go ahead and do that. So let's see if I can draw a straight line passing through most of the points. Okay. So let's put that like so. Bear with me, guys. So I'll do that. Okay. Oops, moved a little bit, but oh well. Okay, so that will do for now. And if I just calculate now the gradient, and I will just go across, and to be honest, I can just use the middle point of the cross and go up along the y-axis. Okay, so that's that. It's not straight, that I notice. Perhaps I should go down, like so. Okay, I'll spare you the details, and let's just go with that. Okay, so with this, if I just calculate the gradient, this is going to be 2.9, and this is going to be minus 0.4, and this value is going to be 0.81, I'd take. Okay, and with those values, I am going to calculate the value of B. So that'll be 2.9 minus 0.4 over 0.81 minus 0.11, and that ends up giving me, it is 3.58, or rather 59, and that is well in between 3 to 4, and that's going to be my answer to B. Okay, now let's talk about the second part, which is using HR diagrams, deduce how the lifespan of hotter stars compare with that of the cooler stars. So we really need to know our Hertzsprung-Russell diagram. So I'm going to draw a sketch over here as neatly as possible, and we know there are many different versions of it, but I'm going to just consider the one which relates to the luminosity. Okay, so luminosity L compared to L of the of our sun. Okay, so the brightest is right at the top, and followed by the dimmest is right at the bottom. And in terms of the x-axis, we have the surface temperature, and we have the hottest stars closer towards the sort of the origin. Okay, and the coolest stars are right here. So this is the surface temperature in kelvins. So it goes something like this, where you have the main sequence belt around like that. Okay, main sequence stars. Then you have your red super giants, and followed by the red giants slightly lower down, and then you have your white dwarf stars right about here. Okay, so it's saying how does the hotter star's lifespan compare with the cooler stars, and it is basically there are two relationships. Okay, first of all, we know that luminosity is directly proportional to the temperature, surface temperature to the power of 4, and we also know that luminosity is proportional to the mass. Okay, so that means that bigger stars have more luminosity, or are more luminous, okay, than smaller stars. And the temperature, surface temperature, is higher as well of more luminous stars. Okay, so they are, so that means the hotter stars have a bigger mass to start off with. So therefore they are going to lose, okay, they will lose mass at a greater rate. Okay, and if they to cool down, okay, so at a greater rate to cool down, so their lifespan is shorter. And compared to the smaller stars. So that's all what, well, I would say about this question. There would be a few marks talking about the equation given to us, comparison with the equation of straight line, working out the gradient, working out the value of b, making sure it's between 3 and 4. Then there would be some marks, I believe, for the HR diagram and relating the luminosity with mass and temperature of the stars, and then finally making points where bigger stars, meaning more luminous, meaning more temperature, meaning higher chance, or rather they will lose the weight, they will lose the mass faster to cool down, hence their lifetime will be shorter. So that is your 6 marker done. Okay, let's move on to hopefully our last question, where we are given that a planet of mass m is in a circular orbit around a star of mass capital M. Okay, cool. And use the equation for Newton's law of gravitation and your knowledge of circular motion to show the relationship between the orbital time period t of the planet and its radius, and to be that. Okay, so this was one of the very common questions that I've seen in the past as well. This is basically Kepler's law, and over here we have to prove it, okay, where if we start off with Newton's gravitation, law of gravitation, which is gmm over r squared, and circular motion, the centripetal force is mv squared over r. To keep an object or a planet in motion, we need to make sure that these two forces are equal to one another, which means that gmm over r r squared is equal to mv squared over r. Dividing both the sides by m, the little m goes away, cancelling both one of the r's, okay, just basically multiplying both the sides by r, which leaves us with gm, this is capital M by the way, leaves it with this being equal to v squared, okay, which v squared is just 2 pi r over t, okay, which is the distance divided by time, okay, distance to complete a, cover a complete sort of revolution, okay, so that's going to be that. Now, if we simplify that further, gm over r equals 4 pi squared r squared over t, okay, t squared, and this basically, we want to make t squared the subject, okay, so let's carry on here. So I'm going to multiply both the sides by t squared. At the same time, I'm also going to divide both the sides by gm, okay, gm, and multiply both the sides by r, okay, so this is going to be r cubed. So because for a given mass of a star, we know m is constant, g is constant, 4 pi squared is also constant, so we can safely say that t squared is directly proportional to r cubed. So problem solved. Okay. Now for part B, it says that the Solar Orbiter satellite was launched in February 2020. This satellite moves around the Sun in an elliptical orbit with a period of 168 days. The diagram below shows the elliptical orbit of this satellite. The closest distance of the satellite to the Sun is this much, and its furthest distance is this much, okay? So furthest and closest. The mass of the Sun is this much, and the mass of satellite is this much. Okay, right, so let's see for part I. It says that the Earth has a mean orbital distance of 1.5 times 10 to the 11 meters around the Sun, and an orbital time period of 365 days. Use Kepler's third law to calculate the mean orbital distance of the satellite from the Sun. So Kepler's third law is what we just proved, right, which is t squared proportional to r cubed. So if I wanted to work out the mean orbital distance of the satellite from the Sun, okay, I know that the satellite is taking, 168 days to orbit around the Sun, okay, and we also know that the Earth takes 365 days. So if you just put that down in a ratio form, we will be able to get the value of r for the satellite. So we can say, right, that r of the satellite cubed over r of the Earth cubed, okay, Earth cubed, is equal, because the proportionality constant cancels out, it'll be equal to time period of the satellite around the Sun over the time period of the satellite, of course, squared, of the Earth around the Sun as well. And we can just rearrange this, okay, to make r sat the subject. Okay, so once we do that, it will be r sat, okay, is going to be equal to that, and we're going to have to just cube root both sides, so t sat over t earth 2/3, and yeah, that's basically put in the numbers of the satellite Earth's radius, sorry, the mean orbital distance, which is 1.5 times 10 to the 11 times by the 168 days over 365 days, 2/3, and that is going to end up giving me a value of 8.9 times 10 to the 10 meters. Okay, right, so for our part II, we are said that the total kinetic and gravitational potential energy of the satellite in its orbit remains constant. Okay, calculate the change in the kinetic energy of the satellite as it travels from its furthest point from the sun to its closest point to the sun. So we know that if you look back at the diagram, the furthest point is right here, and it has maximum gravitational potential energy at that point. And the closest distance is right here, which is going to be maximum kinetic energy. So if we want to calculate the change in the kinetic energy, it will be the same as the potential energy, gravitational potential energy. Okay, so I'll just make it a point that delta GPE is equal to delta kinetic energy, okay, KE or EK, and we know the formula of gravitational potential energy is GM over R, or change in GPE is just change in R. Okay, so pop that into with some numbers. Okay, so the value of capital G is 6.67 times 10 to the minus 11. The mass of the sun is given to us as 2 times 10 to the 30. Lovely. So mass of the satellite is 209. Okay, and that divided by, because it's all just common, so I'm going to consider the change in the distance. Okay, so it's going from basically 4.2 times 10 to the 10 meters to it's going from 1.37 times 10 to the 11 meters to 4.2 times 10 to the 10 meters. And so just to get a positive answer, okay, I am going to put that in the calculator, for which I would end up getting 4.6 times 10 to the 11 joules of energy. So that's that. Finally, last part. Suggest why the total energy of the satellite in its orbit around the sun is not the same as the total energy of the satellite during its launch from the surface of the Earth. Well, that's because of air resistance. Earth's atmosphere, okay, Earth's, okay, atmosphere offers, or will offer, a lot of resistance. And so, a lot more work will be needed to lift off. Okay, so that's the end of the paper, thankfully. I hope you found this useful. If you do have any questions, please let me know in the comments below. I will link the first section of this paper somewhere up in the video, so do check it out if you need to. Have a great day, and I'll see you next time in the next video. Take care, guys. Thanks ever so much for watching.